Hey guys, in today's video I want to show you how to make some Vellum bounce in Houdini, so let's dive in. So I've created a new blank scene in Houdini and the first step is to add a new geometry node. So here I can rename it something like R&D Vellum bounce. I can dive inside and the first step is to import a 3D models. So of course you can use your own 3D model or you can download the final scenes including everything in the link in the descriptions. So here I have my 3D model. It's a Givenchy fragrance model. The first step is to add a transform node. So here with the transform node you can select the node and you can press P to open the parameter of this node. The first step is to add a rotate of minus 90 degrees on the x-axis. And you can also add a rotate of 90 degrees on the z-axis. In that case, you have the bottle correctly placed. So now you can add a match size node to put the bottles on the center of the scenes. And here you can put the target size at 1.25. And you can click on scale to fit. So now you can add a null to specify this is the input geometry. So you can rename it something like out geo. So now you can place this bottle a bit up on the y-axis. So to do that, you can add another transform node. And here we will change the value. So in my case, I will change the translate on the y-axis to 3.25. In that case, you have the bottle right here. And you can add a bit of rotate to get something a bit more natural in the movement. So here you can change the rotate on the y-axis to 13. You can change the rotate on the y-axis to 5 and the rotate on the z-axis to 7. In that case, you have these orientations for the bottles. So now let's add the blast node. So in this bottle, you have basically everything. So you have the liquid, the inner parts, you have some fabric here, metal pieces here. So for the simulation, we will use a proxy geometry. So basically we will use only the glass and the top parts. So to do that, we'll use a blast node. So here with the blast node, you can select the part you want to keep for the simulations. So with this little icon, you can select the different parts of the models. In my case, I will keep the cap, I will keep the glass, and I will keep the top. So now I can click on delete non-selected. And in that case, I have only this part for the models. So now you can convert that to VDB. In that case, we can create one and single geometry because for now we have three parts of the models. We have the glass, we have the top part, and we have the cap. So let's create one and single geo. So to do that, you can use the VDB from polygons. Here with the VDB from polygons, you can reduce the voxel size to 0.1. Now let's use the VDB reshape SDF. And you can keep the operation to delete and you can keep the offset at 1. Of course, it's up to you. It depends on your geometry. Maybe you have to change a bit this setting so you can increase the offsets, or maybe you have to use the erodes operation. So it depends on your geometry. So now let's add the convert VDB node. And here with the convert VDB node, you can select the convert to polygons. In that case, we can convert this geometry back to polygons. And now you can put the adaptivity to 0.1. So now you can add a smooth node. And here you can add a null to specify this is a proxy geometry for the simulations. And you can rename it something like proxy geo.
Imagine having access to over 40 hours of exclusive Houdini tutorials. And that library keeps growing every month with brand new content. On Artilabs, you'll find in-depth Houdini tutorials covering motion design, simulations, product visualization, and more. Plus, you get access to all project files so you can follow along step by step. And right now, we're offering an extra 20% off the annual membership, on top of the 10% discount already included when compared to the monthly plan. This exclusive deal is available for the first 30 people, so don't miss out. Click the link below, your 20% discount is applied automatically. Secure your spot before it's gone.
So now let's add a box for the grain simulations. So let's add a box. You can display the box and maybe you can template the proxy geometry. So now you can change the size of the box for the simulations. So you can change the x-axis to 6, you can keep the y-axis to 1, and you can put the z-axis to 4. Of course, it's up to you. You can change this value if you want to get something more big or a bit smaller. It depends on your simulations. So now let's add a match size node. And here for the match size node, you can put the justify y to minimum. In that case, you can put the box on the floor. So now let's create the Vellum grains based on this box. So to do that, you can use the Vellum configure grains. And here with the Vellum configure grains, you can click on create points from volume. In that case, it will create all these grains. And here you can change the particle size to 0.05 to get a bit more points. Here you can enable the jitter scale. Of course, it's up to you. If you want to get something a bit more symmetrical pattern, you can keep this one disabled. But in my case, I will enable the jitter scale and I will put the value at 1. In that case, you have this kind of result. And I will also tick these options to avoid overlap between the different spheres. So now you can open the physical attribute and later we will change some value here. But for now, let's keep everything by default. So now we have the grains. So now let's create a Vellum constraint to get some glue between each different grains. So let's add a Vellum constraint. And here with this Vellum constraint, you can select the glue constraint. And to visualize this constraint, you can add a null on the constraint here. So this is just for these, so you can rename it something like these. And now you can enable this one, and you can see for now we don't have anything because on the Vellum grain constraints, you have to select points here for the group type, and for the target group type, you have to select points. So now you can see that we have some glue constraint created here. Maybe you can put the background in dark. So to do that, you can press D, you can go to background, and you can put that in dark. So now you can see that we have some glue constraint created here. For now, we don't have in-house constraints, so you can just go to the constraint settings, and here so for the constraint per points, you can increase it from 1 to 10. And if you go to the Vellum Grains node, if you disable the jitter scale, you can see that you have something way more symmetrical pattern. So it's up to you if you want to get this one enabled or disabled. So now we have our grain on the left side and we have our collider geometry on the right side, but we need to convert this collider geometry to Vellum to get some nice movement between the grain and the collider geometry. So now let's add another Vellum constraint. And here you can plug this collider geometry to this Vellum constraints, and you can convert this geometry to Vellum shape match. In that case, we can get some kind of rigid body stuff in Vellum with a shape match constraint. So now let's add 3 merge nodes. 1, 2, and 3. So in the first one, we can plug the geometry. In the second one, we can plug the constraints. And in the third one, we can plug the collider. So let's select the geometry of this one and this one. Plug them into the first merge node. Let's select the constraints. Plug them here. And let's select the collider. Plug them here. Now let's add Vellum Solver node. And now we can plug the geometry on the first input, we can plug the constraint to the second input, and we can plug the collider to the third input. So now for the Vellum constraint, we can select the Vellum constraint shape match, and here for the mass, you can set it to uniform, and you can put the value at something like 0.25. So here for the Vellum constraint grain, you can play with different settings if you want, but in my case, I will put the mass here to 0.5. I will change the frictions to 0.5, and I will also put the repulsion weight at 2. Of course, you can change this setting if you want, and you can make them a bit different to get different results for the simulations. And for the Vellum glue constraint here, you can keep everything by default. Of course, it's always up to you if you want to change the stretch value. So in my case, I only change the constraint per point. Instead of 1, I put the value at 10. So to get this kind of bounce interaction between grains and between collider geometry, it's all about mass. So we need to change the mass over time inside the Vellum Solver. So to do that, we can create a group for the collider geometry. So let's add a group node. And you can plug the geometry output of the collider geometry to this group node because mass is a point attribute. And here for this group, you can rename it something like collider. And you can put everything in this group and you can change it to point group. So now you can remove this link by pressing Y on the keyboard and you can replace it with the group node. In that case, we have a group created for this collider geometry and we can manipulate the mass attribute inside the Vellum Solver based on this group. So for the Vellum Solver settings, I keep everything by default, but of course, one more time, it's up to you. You can play with substeps, constraint iterations, and smoothing iteration if you want. The only thing I change is under the simulation tab, I increase the cache memory here to get a bit more preview. So now let's see the result of what we get at the moment. Of course, don't forget to go to the Solver tab and enable the ground position. In that case, we can create a ground for the simulations. So this is what we get for now. So I have this kind of bounce stuff. So now we can manipulate the mass value for the collider inside the Vellum Solver. So to do that, you can dive inside the Vellum Solver and you can add a subsolver. And you can plug the subsolver to the source. So now you can dive inside the subsolver. And here you can select the dop geometry and you can add an attribute angle. Here you can plug that here and you can manipulate the mass for the bottle only. So to do that, you can select a group and we have created a group called collider. So you can select the group here. And now you can manipulate the mass attribute. So I will show you 3 different ways to manipulate the mass attribute. The first one is very easy. So you can just type f at mass is equal to channel float. And here you can create a little channel for the mass. So you can rename it something like mass value. And here you can press that and you can click on that to create the channel. So basically what you can do, you can put first value here, so you can disable the simulation by clicking on these icons, and you can put the mass value at 0.05. You can add a keyframe, press Alt and left click at the frame 1, You can go at the frame 48 and you can put the value, let's say at 0.8. Press Alt and left click and you can go to the frame 96 and you can put the value back at 0.05. So now you have this kind of curve for the mass value. So the mass value will change from 0.05 to 0.8 and go back to 0.05.
Ready to level up your Houdini pipeline? Get the Houdini Script Pack. Complete toolkit, 7 powerful tools today, plus every future release with free updates. Save time on composition, geometry splitting, material creation, and more. YouTube subscribers get 50% off with code TOOLKIT. Click the link in the description and transform your workflow today.
So let's see the result of the simulations. So now you can see the result of this simulation. The highest value for the mass is at the frame 48. So let's click on play. And you can see that we have the mass here, and now the mass start decrease and go there. So you can play with different value with the keyframe and curve like this. So this is the first method to adjust the mass value over time. So the second method is to remap a time value. So let's add another attribute wrangle. You can plug the dot geometry into the first input and you can plug that to the output of the subsolver. So here don't forget to select the collider group one more time. And here the first thing is to create a float t which is equal to @frame. In that case we can get the value of the frame over time. Now we can create a float mass minimum value which is equal to channel float, and you can create mass min. Let's do the same for mass maximum value. So you can copy that, paste it here, and you can replace the name of minimum with maximum, and same for this one, mass maximum. Now let's do the same for the frame. So you can create a minimum frame and maximum frame. So let's create an integer value for frame min, which is equal to channel I, and you can type frame min. And let's do the same for frame maximum. So you can copy that, paste it here, and you can replace the name of minimum with maximum. And now let's adjust the value of the mass based on the frame value. So let's type f@mass is equal to, and you can use the fit functions with our t variables. And here you can type frame min, frame max, and you can remap that for mass min and mass max. And now if you want, you can clump that. So you can use a clump, and you can clump it from mass min to mass max. So now you can create all the channel by clicking on this, and let's say that we want to the mass minimum value at 0.01, the mass maximum at 0.6, and let's say the frame minimum at 1 and the frame maximum at 48. In that case, we can remap the value between the frame 1 and the frame 48. Of course, it's up to you. You can change the minimum frame at the frame 24. It's fully up to you for this value. So now let's see the result of this second method. So you can see that the mass value starts growing over time. So the value basically at the beginning of the simulation, the value of the mass is at 0.01, and the value of the mass at the end of the simulation is at 0.6. So now you can remap the value of the mass based on the time. So this is the second method to adjust the mass value here inside the subsolver. And the third one is my favorite, and this is the one I used for my render simulation. So let's add an attribute wrangle. Let's plug that to the first input and plug that to the output. And here under the group, you can select your collider geometry. And now you can type f@mass, which is equal to channel float, and you can type mass. And now you can create the channel. So this is the same as the first one. But now let's select the mass value here and click on motion FX, and you can select wave. So the value of the mass will change from up to down over time like this, and you can adjust the value very easy with these different settings. So here for the offset, I will put the value at 0.275, maybe 27, something like this. And I will change the amplitude to 0.4. So now you can see that the value goes at the minimum at something like 0.2 for the mass, and go at the maximum at something like 0.8. Maybe you can put that to 0.26. So of course it's up to you. You can change it like this. And you can also change the period if you want to get the variation faster or slower. Maybe you can put the value at something like 0.95, and I think it's good. So now we have the mass value will change over time based on this sine wave. And let's see the result of this third method. So now let's see the result of this third method. And now you can see that we have the mass value will change over time. Of course, you can change different settings on the Vellum constraint grains. You can change the mass of the grains. Of course, it will change the results of the simulation, and you can also change the different settings here if you want. So this is the three methods you can use to get some bounce interaction between the collider and the grains. So let's use this last method for the render. So now let's do the post-processing to get some nice results. So let's take the constraints of the Vellum Solver. Let's add a split node. Now you can see that we can get the result with only the constraints, so it removes the geometry. And now let's select only the grains and remove the bottle. So to do that, you can select the Vellum constraint 1, and in that case, we can get only the grains. And now you can put that in cache if you want. So let's add a file cache node, and you can type something like lines out, and you can put that to explicit. You can put that into a cache folder and into $OS folder. And here you can put the range you want to put in cache. So maybe you can right click, delete channels, and you can put that from the frame 1 to the frame 144. So you can click on save to disk. In that case, it will save this simulation in cache. So now you can see that we have used a proxy geometry for the simulation, but of course for the rendering, we have to use the high-res geo, which is here. So to do that, you can select the geometry output of the Vellum Solver, and let's add a split node. And here with the split node, you can select the Vellum object 1. In that case, we have only the bottles. Now let's add an attribute wrangles. And let's put a class attribute. So here you can type e at class is equal to 0. And now let's add a null object, and we can rename it something like geo. And now to use our original bottles, you can take this transform node. Let's add a null here. And you can rename it something like orig geo. So now let's add the class attribute with the value at 0 like we did before for this one. So you can copy the attribute wrangles with the e at class at 0 for these original bottles. So now let's add a point deform. In that case, we can deform our original geometry based on the proxy geometry. So let's add a point deform. Let's plug this one to the first input. Let's plug this animated geo to the third input. And let's add a time shift node. And here let's freeze the animation at the frame 1. So right click, delete channel. Plug this proxy geometry to the time shift, and plug the time shift to the second input of the point deform. So now you can see it will deform our original geometry based on the proxy geometry. But you can see that we have some little issue here. So basically here we have some little problems. So here on the point deform, we can select our piece attribute, and the piece attribute is our class attribute. And here you can change some settings on the point deform. So you can change the radius at 1. In that case, we have something a bit better. And you can increase the maximum points to 5,000. It's a bit slow, but you can see now we have very, very clean bottles. So now you can add a file cache node for this one, file cache. And here you can rename it something like out orig bottle. So here you can click on explicit, and you can put that in cache and into $OS folder. So now you can put that in cache for 144 frame, delete channel 144. And you can add a null to specify this is the output of the bottles. So you can rename it like out bottle. So if you want, you can create a mask from the bottles to create some nice color for the rendering. So to do that, you can add a mask from geometry. Here you can put the line on the first input, and you can put the bottle geometry to the second input. So let's add a smooth node. And let's put that to the second input of the mask from geometry. And here you can preview the mask by clicking on the information tab here, and you can enable the mask. So now you can see it will create a mask attribute. So now you can see that we have a nice mask created by the bottles. And if the bottle go up, for example, at the frame 4, you can see that the mask value will change. So it's very, very nice option to get some nice color for the rendering part. So here, of course, you can change the radius if you want. So you can put the value at something like 1.25, and you can select this and put that to linear. And now we have this mask. So you can use this mask value in Redshift or Octane to get some cool color for the rendering part. And if you want, you can add another file cache here, and you can rename it something like final line. And you can put that in explicit, and you can put that in cache folder and $OS folder. And here you can add a null to specify this is the output for the line, and you can type lines. So now you can create a geometry container for the line, geometry container for the bottles, and you can render everything. So if you are using Redshift, you can render this line as here. So you can just select your geometry container, you can go to Redshift object, and here under settings, you can enable render polygon as here. And if you want to use this mask point attribute for Redshift to get some nice color for the rendering, you have to promote it from point to primitive. So let's add an attribute promote. And here you can promote from point to primitive, and you can select the mask attribute. So now you can use it to get some nice color for the rendering. So that's it for today, guys. I hope you enjoyed it. See you in the next one. Don't forget you can buy this project file in the link in the description with all the YouTube tutorials project files. See you in the next one. Bye-bye. That's it for today, guys. Thanks for watching, and don't forget to subscribe to our channel and check artivoxa.com to get premium 3D resources. You can access to this project file with our Artifiles membership. See you in the next one. Bye.